Good morning, everyone. Thank you for being here. It's a really pleasure for me to be with you today and to hold this seminar in collaboration, as Giovanni said, with the Department of Human and Social Sciences, Culture, Heritage. I want to warmly thank the director of the department, Professor Salvatore Capasso, for the invitation and for supporting this initiative. As you already know, the topic of the seminar today is text as data, the potential of large language models in social research. My aim today is to present these tools in a simple and, more importantly, in an accessible way, without assuming any prior technical knowledge. And to show how these models can be used concretely in social science research, including, I guess, the kind of work many of you might do. But before I begin, let me briefly walk you through the agenda for today. I have designed the seminar in two main parts. In the first part, we'll look at the core concepts behind large language models. The goal is to simply try to give you an intuitive understanding of how these models work and why they recently represent such a major shift for text-based research. In the second part, we will move to the practical applications. Here I have chosen firstly two research papers that are applications from the recent literature to illustrate how large language-based methods can be used to support any kind of research. These two papers come from recent work in economics and political science, but to my opinion, the underlying ideas that they give to us can be applied across many other disciplines. And I will also show you a real example from my recent work using the OpenAI API for information extraction, which is part of the ongoing research project with the name Potion, Policies for Transition, Impact and Governance, in which I am currently enrolled. To begin exploring how large language models work, I think that it's helpful to take a quick look at how we got here over the last 30 years. In 1990s and in early 2000s, models looked at only at a small sequence of words, what we call usually n-grams. They just counted how often words appear together. Around 2013, we had the first major innovation with the model Word2Vec. It was for the first time that words were represented as vectors. So the vectors, I mean numbers that can capture their semantic similarity. Soon after, around 2014, more complex neural models appeared. I can mention here RNN or LSTM. These networks could handle longer sequences, but still they struggled with large amounts of text. And it was in 2016 that something truly transformative, I can say, happened, the introduction of the transformer architecture. This is the foundation of almost all modern language models that we use today. From 2018 onwards, we see the explosion of pre-trained models. It was in 2018 the presentation of BERT model that it is excellent for understanding text. BERT stands for bidirectional encoder representators from transformers, and there were other models such as GPT-2 and GPT-3 that are able to generate text. And eventually, models like ChatGPT, GPT-4, and the last one, GPT-5, which many of us, I guess, already interact with. Now, let's start clarifying what large language model actually is. At its core, a large language model is an artificial intelligence system trained on massive amount of text, such as books, articles, websites, and so on, to learn how language works. So the model becomes extremely good at predicting what words should come next in a sentence. This is the key idea behind models like GPT, next word prediction. So the model simply computes the probability for each next word based on previous words. That's why we call them autoregressive language models. The same mechanism can be used in two different ways to contain a sentence, which is what GPT models do, and to fill in missing words, which is what models like BERT are trained to do. Now that we understand how the model predicts the next word, let's look at what really happened when it makes that choice. As I said, for every possible next word, the model computes a probability. This probability is influenced by how often that word appears in similar contexts during training. But there is always some randomness. The model does not always choose the most probable word. Instead, it chooses from a whole distribution of options. For example, let's understand in a simple example. If we give the model the beginning of a sentence, let's say like the sky is, it generates for us a list of possible continuations. Perhaps blue has the highest probability, and clear or cloudy have lower probability. So the model sees all these options and picks one according to these probabilities. This means that each time you ask the same question, the model may give slightly different answers, because what it is doing, it is sampling from this probability distribution. This is the reason why the output sometimes feel flexible or sometimes creative. But how exactly does the model choose which word or to generate from that probability distribution? There are different selection strategies that influence how predictable or how creative the output will be. I will start with the most important one, which is temperature. It controls the level of randomness. If we set a low temperature, like 0 or 0.2, the model becomes very conservative. In this case, it will mostly choose the words with the highest probability, giving to us more stable and predictable answers. If we increase the temperature, let's consider the fact that the temperature takes the values from 0 to the maximum of 2. Let's say if we put the temperature to 1 or above 1, the model becomes more adventurous, selecting less common words and producing more diverse or creative outputs. In some way, temperature is basically a creativity deal. The second technique is greedy sampling. This is the simplest method. The model always picks the most probable next word. So this makes the text predictable and sometimes repetitive. It's like always choosing the safest option. The third technique is top case sampling. With this way of sampling, instead of considering all possible words, We limit the choice to the top k most likely ones, maybe, for example, the top 10 or the top 15. This keeps the output sensible, but still allows some variation. It's a way to balance coherence and creativity. As I mentioned before, the architecture that made modern language models possible is called transformer. The key innovation is that transformers can look at all words in a sentence at the same time and evaluate how much each word matters for interpreting the others. This ability to consider the full context rather than just the previous words makes them much better in understanding relationships, meaning, or the structure in language. There are three main families of transformer models. The first one, encoder models like BERT, which are excellent for understanding text. The second one are decoder models like GPT family, which are designed to generate text. I will explain to you what I mean with encoder and decoder in the next slides. And we have both encoder and decoder models like T5 or BART, which can both understand and produce text. Most of the languages, modern languages that we use today, including ChatGPT, are based on the decoder architecture. Now, let's move to the core mechanism inside the transformer that is called self-attention. Despite the name, the idea is actually, let's say, very intuitive. For every word in a sentence, the model learns to pay attention to the other words that are most relevant to interpreting it. This formula in this slide describes it, but the intuition is each word creates three vectors, the vector of query, key, and value. And the model uses this to compute how strongly each word should attend to every other word. The output is a kind of a weighted summary of the information in the sentence adapted to each word's context. Now, let's have a look at how this works in practice, and in order also to understand it. Let's take an example with the sentence, "The fisherman sat on the river bank." As we know, the word bank is ambiguous because in some cases it could be a financial institution, or in other cases it could represent the side of a river. Through self-attention, the model assigns more weights to the word river when interpreting the bank. You can see in this table here, it's a demonstrative example, that bank attends strongly to river and less to other words, the, set, or on the. So the model chooses the geographical meaning simply because the context points to that in that direction. This is what makes modern large language models so good at understanding polysemy in the cases that that words have multiple meanings. Now, if we change the sentence, the tension pattern changes completely. In the second sentence, "She deposited money in the bank." The relevant words for interpreting bank are deposited and money. So we can see here that in this table that bank now attends strongly to those words and not to she or in. So the important message from this example is that the meaning of a word is not fixed, as we already know, but it is constructed dynamically from the context using self-attention. But it's not only self-attention. One final piece completes the whole picture, the so-called multi-head attention. Instead of computing one single attention pattern, the model computes several of them in parallel. These are called heads. Each head specializes in a different type of relationship. Let's say one may focus on syntax, another on semantics, another on location, or the order of the words, and so on. After processing these perspectives in parallel, the model combines all of them. This gives us a much richer, more nuanced understanding of the whole sentence that a single attention map could provide. So this is what the multi-head is adding in this case. To understand how multi-head attention works, I have prepared this concrete example. We have always the same sentences. In the first sentence, the fisherman sat on the riverbank. With riverbank, we have three different heads. The first one focuses on syntax. Who does what? In this case, fisherman said. The second head is focused on the meaning. So river is related to the bank. And the third head focuses on the order in the sentence. In the same logic, in the financial sentence, in the second table, the roles shift to highlight the relationship relevant to the new context. Okay, now let's briefly look at how these models actually learn. This is important to know. The model learns by predicting the next word, as we said, and correcting itself. During training, the model sees a huge amount of text. For every position in a sentence, it tries to guess the next word. If the guess is wrong, which happens millions of times at the beginning, it adjusts its internal parameters slightly. These tiny adjustments accumulate over trillions of predictions, and step by step, the model becomes better at language. So the model is learning by doing mistake, as we do, as we humans do. That's what the loss function means. It's just a measure of how wrong the model is. But not all the models learn in the same way. GPT models learn by predicting the next word, as we said, and BERT models learn by filling in missing words, for example, completing a puzzle. Beyond the basic learning process, more modern models like GPT-4 and GPT-5 also learn from human feedback. This is called reinforcement learning from human feedback. What this means is that humans rate different model answers, and the system learns which behavior is more helpful, polite, or accurate. Now, let's look at what actually happens when we give a sentence to a language model. If we write in plain English or in whatever language we use, sorry, the model cannot work directly with words. It needs numbers. So the first step is to convert text into format the model can understand. Here I have chosen another sentence, a simple one to understand the logic. Let's take the sentence, the patient reports pain. Several transformations happen before the model can process this sentence. The first step is encoding. What this means, first every character of each word is turned into Unicode number. This is a very low-level step, simply turning letters into digits. Then the second step is broken these words into tokens. What is tokenization? Is the process of broken the words into tokens. A token could be a word or a subword. It depends on the tokenizer we are using. In this sample, we have four token equal to 4 words. And later on, each token is then replaced by a numerical ID from the model's vocabulary. For example, passion becomes the number 5023, pain becomes 921, and so on. Next, the next step, each token ID is mapped in a dense vector, what we call an embedding. What is embedding? This vector is a numerical representation of the token's meaning learned during training. Tokens that appear in similar contexts, let's say pain and ache, have vectors that close to each other. And finally, the last step, after processing, the model converts vectors back into text. So there is a continuous movement from text to numbers, to vectors, to numbers, and finally to text. Now, the next question is how we do measure whether two words are similar. One of the most common tools is cosine similarity. What it measures? Cosine similarity tells us how close two vectors are in direction, regardless of their length. This is the formula that calculates it. In other words, it captures how similar the meanings of two words are. Cosine similarity takes values from -1 to 1. If it is -1, this means the opposite meaning. Two words have the opposite meaning. If cosine similarity is 0, two words have no relation. And if it is equal to 1, this means that they are, let's say, identical. They have the identical meaning. Here, I have prepared a simple demonstration to understand the cosine similarity. Two vectors represent the word woman and lady. Their cosine similarity is extremely close to 1, what means that the model sees them as almost identical in meaning. On the other hand, the similarity between girl and rocket is much lower, in this case around 0.6. So this means the model considers these two words unrelated, which makes also sense semantically. Now I want to move to another direction, to the ways how we can represent text into numbers. Before modern embeddings existed, one of the earliest way to represent text numerically was the bag of words model. The idea is extremely simple. For each document, we count how many times each word appears. So, instead of worrying about elements such as grammar of word order, a bag of words creates a big vector where each position corresponds to a word in a vocabulary, and the value is just the count of that word in the document. This procedure is something that produces what we call high-dimensional sparse vectors. It is high-dimensional because the vector has one entry for every unique word in the whole corpus, and it is sparse because most entries are 0. Each document only contains a small subset of all possible words. Bag of words was useful. It was useful, but it represents the first step in natural language processing because it captures which word appear and how often. But it does not capture the meaning or the context or any relationship between words. Now, I have prepared a simple example to see how bag of words work. We take always the two sentences. The fisherman sat on the riverbank and she deposited money in the bank. We first create a vocabulary with all unique words across both sentences. Here, in this case, we have 10 terms in total. Each sentence is then transformed into a vector of length 10. For each word in the vocabulary, the vector stores a value of 1 if the word appears in the sentence and 0 if it is not there. So if we can have a look at the vector for the first sentence, it has ones in the positions corresponding at the words in this sentence, and the same thing for the second sentence. But although the word bank appears in both sentences, in one case it means, as we know, the side of a river, and in the other it means the financial institution. Bag of words puts both accuracies in the exact same position in the vectors, completely ignoring meaning and also the context. Now, let's move to an improvement, let's say, over the simple bag of words model we just saw. It is term frequency inverse document frequency, or shortly TF-IDF. This method has two key ideas. The first one, words like stop words such as the, in, or, and others that appear everywhere, they are not informative. So what TF-IDF does with this kind of words, it reduces their importance by giving them a low weight. And the second key idea is that if a word is frequent in one document, but it's rare across the whole collection, TF-IDF gives it a higher weight. This helps identify what is specific or characteristic about each document. So TF-IDF tends to work much better compared to the plain bag of words for tasks like, let's say, classification or clustering, but in the same time, it still shares the same limitations as bag of words, because the vectors are sparse and the method is context independent. Now let's see TF-IDF applied in the two example sentences. In this tiny corpus, we have two documents. That makes I choose this only to make the calculations straightforward. We notice that the word bank gets weight 0 in both sentences because it appears in both documents in this case, and is therefore not informative for this model. So once again, TF-IDF still cannot distinguish between the two meanings of bank. The methods improves bag of words as we saw by emphasizing important words, but still ignores the context and also the meaning. So sorry. Now we move to another important family of representation of words into numbers. It is static word embeddings. Up to this point, we saw bag of words and TF-IDF, which are sparse and context independent. Static word embeddings improve on this by learning dense vector representations that capture semantic relationship between words. So the key idea is simple. Each word gets one fixed vector, regardless of whether it appears or what meaning it has in the sentence. These vectors are learned from co-occurrence patterns in large text corpora. The model essentially noticed which words tend to appear near one another and adjust their vector representations so that related words end up close together in a vector space. What these embeddings give us, they capture word-level semantics. It is a famous example that this model can understand. If we take the vector of king, minus the vector of man plus the vector of woman, the model understands that this is equal to the vector of queen. So these models are computationally efficient and work well with moderately sized datasets. This is why these models become extremely popular before transformers. But one limitation remains also in these models. They are context independent. For these kind of models, the word apple has the same vector whether we are talking about fruit or about the technology company. Here, I have prepared a concrete example to see what static embeddings do and what they cannot do. Here, always we have a few words from our earlier sentences, each assigned a fixed vector. Notice especially the vector for bank, whether the bank appears in the sentence about a river or in the sentence about the financial institution, the vector remains exactly the same. So this example illustrates also the core limitation of these models. Static embeddings cannot distinguish different meanings of the same word. In this case, homonyms collapse into a single vector. However, within this limitation, they do something very powerful. What they do is that words like with similar meaning end up with similar vectors. For these models, river might be close to stream, king might be near to queen, or doctor might be near to nurse, and so on. So this is something that TF, IDF, or bag of words cannot do at all. In these two models, the river and stream was completely unrelated or orthogonal. So static embeddings give us semantic similarity, but they cannot give us contextual meaning. Now, let's move to the type of models that can give us the contextual meaning. These are contextual embeddings, which is what modern transformer models like BERT or GPT actually produce. The key idea is simple. Each word no longer has one fixed vector. Instead, its vector changes depending on the words around it, as I explained in the slide about transformers. So if we look at a word at position T, the model computes its embedding by looking at the entire context, the words before and after, using the self-attention mechanism we saw earlier. These contextual embeddings are what give transformers the state-of-the-art performance, because they understand not just isolated words, but how words interact in a sentence. Here is always a demonstration of how contextual embeddings work. We again compare the two sentences as before. With self-attention, the model assigns different weights to the surrounding words. When we combine these context-weighted vectors, we get two completely different embeddings for bank. And if we compute the cosine similarity between them, it is very close to zero, meaning that the model, finally, let's say, has successfully distinguished the two meanings. So this ability to adapt the meaning of a word to its context is what makes contextual embeddings very powerful than other techniques that we mentioned, such as bag of words, TF, IDF, or even word2vec, that is a static embedding. But there is more. So far, we have focused on embeddings for individual words. But very often, and also in social science research, what we actually need is the representation of the entire sentence or the entire paragraph or the entire document. So to do this, we can combine all the token embeddings into one single vector. There are two common strategies I want to mention. There are also more others, but I will mention only these two that are the most important one. Mean pooling. What we do is simply average all the token embeddings. This is simple and surprisingly also effective. And the second one, more complex, is CLS pooling. This is used by BERT models. Here we use the embedding of a special classification token that the model learns to place at the beginning of the sentence. So to understand it, CLC is not a real word. It means this is the beginning of a sentence. Please create an overall summary here. And the model, in this case, writes a mini summary into this CLC token, and we use that directly without averaging. So the result is a compact vector, typically a few hundred or let's say 1,000 dimensions, that captures the overall meaning of the whole text. These sentence embeddings are used for many tasks in research. I can mention similarity search, clustering, topic exploration, and also semantic matching. Sentence and document embeddings have several important advantages. They can give us dense, compact representations that still capture a rich meaning. They work extremely well for similarity tasks, as I said. But however, these have also some limitations because they require large pre-trained models, which can be also computationally expensive. And because the embeddings are dense vectors with hundreds of dimensions, it is harder to interpret the output from them compared to simple models like, let's say, TF, IDF. Now, let's move to something different that is related and very important when we talk about large language models, into prompt engineering. I have chosen this famous tweet by a former researcher at OpenAI and Tesla that captures the idea of what prompt engineering is, I think, perfectly. So, large language models, with large language models, we no longer write code in Python or in Java or in other softwares to get something done. What we do is we write instructions in natural language. So prompt engineering is simply the practice of writing those instructions in a smart, structured way so that the model produces the most useful output. Now, to understand what prompt engineering is and is not, it helps to compare it with fine-tuning. Prompting is what we do every day, let's say with ChatGPT. We give the model instructions written in natural language. What I want to highlight is that prompting does not change the model itself. It only changes the input. So what we guide the model to behave in a certain way. In contrast, fine-tuning is something actually modifies the model's internal parameters because when we do fine-tuning, we take a pre-trained model and train it further to a smaller or specialized data set. This changes its weight, so the model becomes adapted to our specific task or our domain. Why I'm saying this for you. It's because this makes prompting accessible to everyone and fine-tuning something more technical and resource intensive. Now, after saying that large language models are so powerful, they can understand meaning, finally, I think that it's crucial to clarify what large language models are not. They don't understand language in the human sense, or at least up to today, they don't understand language in the human sense because we don't know what they might do tomorrow, let's say. This is a very dynamic field. Instead, what they do is they operate by detecting statistical patterns in enormous amount of text. This gives the impression of compensation, but what they fundamentally do is that this is a pattern recognition at very large scale. Why I am emphasizing this? Because this distinction helps us manage our expectations about what large language models can do and cannot, and why they sometimes produce brilliant insights and sometimes make very strange mistakes. So this is important to understand. Now let's move to the limitations of large language models and what they mean for us as researchers. A first major challenge is data privacy. Large language models may process sensitive or personal data, as we know, and if we upload, let's say, text without checking it before, we risk exposing the information that should remain confidential. Even when we anonymize documents before, certain details may still indirectly reveal some identities. And finally, if data is processed in the cloud, this can trigger GDPR issues, especially when data crosses borders. So, okay, these are the limitations, but to manage them responsibly, the best practices I think that are quite straightforward. Before we use LLMs, we should remove or anonymize any identifiers. We can process data locally whenever possible if data privacy is a concern. We can use on-premise or open source models, and also we can choose GDPR compliant providers. So there are some steps that we can do. Another limitation I want to discuss is the quality of the information that LLMs produce for us. These models can generate text that sounds extremely convincing, but maybe incorrect. That's what we call hallucinations. The best way to prevent this is not simple to do, but we can constrain the prompt so that the model stays within verifiable information. For example, if we are extracting data, we can ask the model explicitly extract only facts present in the text. We should also verify outputs manually or with automated fact-checking tools. And importantly, we can set the temperature equal to 0 or low values to make results more consistent, and we can also add some validation scripts to detect suspicious outputs. A third limitation I want to discuss is bias, which is a very real problem because what large language models do, they learn from human-generated data. This means they can reproduce and even amplify existing social, gender, cultural, or also racial stereotypes in the society. The example on this slide shows how the model tends to associate certain professions with specific types of people. This is not intentional, but it reflects the patterns in the data the model was trained on. When these bias enter our research, they can in some way distort insights and potentially mislead policy conclusions that we can do. To mitigate this, we need to test for bias explicitly across different demographic groups and different contexts. And when we fine-tune models, we should rely on balanced and domain-specific data sets. It is also Also very important to document limitations transparently and involve human reviewers when results involve sensitive or subjective topics. Another important limitation is explainability. As we know, large language models are artificial intelligence models and they behave like black boxes. We see the output, but we don't have access to the full internal reasoning step. This makes it hard for us to understand why the model produced a certain answer, and also even harder to replicate the same reasoning path later. So, to increase transparency, we should log all prompts, all the parameters, and model versions for every experiment that we run, just as we do with statistical elements in traditional research. Or maybe also including an appendix with AI documentation can greatly improve reproducibility. Sorry. And the final limitation I want to discuss with you today, there are lots of other limitations of LLMs, is reliability. LLMs are probabilistic, as we said, so small changes in the prompt or the context length can alert the output. This means results can be inconsistent or non-reproducible. To improve reliability, we can fix the model seeds and also the versions that we use so that we can repeat the runs and have consistent output. How we can do it? Using, for example, frozen model versions updated to a specific date can avoid changes versus the use of online version that change the training over the time. And as always, for any critical research step, we should keep a human in the loop for review. Now, I want to look together at how large language models are actually being used in social science research. There are lots of ways how we can use large language models. I will mention only some of them, starting from the most common use of large language models in social science research is extracting structured information from unstructured text. This is especially helpful when working with large corpora, such as policy documents, interviews, media reports, and so on. Large language models can help us automatically extract entities, events, sentiment, policy measures, or even attitudes, essentially when the data is messy into text. A second major application is classifying text into categories such as sentiment, topics, or also themes. With large language models, this can be done in a zero-shot manner. What this means is that no training data is required, only with a prompt, or with a few shots that we provide some examples, or embedded-based classification method that can add precision. This makes large language models extremely useful for survey coding and also document labeling, where researchers often need to categorize, let's say, thousands of open-ended responses or document quickly and consistently. A third application of large language models in the research is using them as prediction using text. As I explained to you, large language models allows us to convert text into numerical embeddings. So these embeddings can be used as input features in traditional statistical models, and this enable prediction on real-world outcomes, such as innovation potential, employee turnover, or let's say macroeconomic indicators. We will see together an application for using large language models in prediction models. Also, LLMs could be used for content generation and data augmentation. This means that LLMs can generate synthetic text that helps researchers overcome sparse or unbalanced datasets, for example, by producing examples for rare events or underrepresented groups. They are also increasingly used in the recent literature to generate counterfactuals. What this means that we ask them, what if this policy has changed, or how would this actor respond under a different scenario? Additionally, researchers can simulate survey or interview responses to run robustness checks or explore alternative theoretical scenarios before they can conduct very expensive field work. The last one I want to mention, in fact, this is the first step we do when we conduct research, is data processing and pre-processing, data cleaning. Large language models can assist also in this step because they can help, for example, standardized names, locations, entity references. They can fix OCR, optical character recognition, errors, or clean documents with inconsistent formatting. So, in short, large language models serve as a multifunctional assistant that can help us in every stage of our research. Okay, now let's move to the second part of the course in the practical part. Here, in the first, this is the first paper I've chosen to present today. This is a recent paper published in the American Political Science Review. It is titled Embedding Regression, models for context-specific description and inference. Let's see what other researchers has done using large language models. Why I have chosen this paper for today? In my opinion, this paper serves a lot because one of the core challenges in social science is understanding how meaning changes across groups or over time. Traditional natural language processing tools struggle with these problems. They often require large data sets and they don't allow us to make statistical claims, things like confidence intervals or hypothesis testing. The contribution of this paper is to show how we can use large language model embeddings as regression outcomes. That means we can model meaning differences across contexts in a way that is also statistically testable. So, how does this work in practice? First, the model starts with a pre-trained embedding model. In this case, the authors have chosen GloVe. This is a static embedding. This gives us the basic factor for each word, kind of starting point for meaning. Then we collect every occurrence of our focal word of the interest in different contexts. For example, let's say if the word that we are interested in is immigration in democratic versus Republican speeches. Next, we extract the context embeddings. These represent the words surrounding the term, the target term, and give a sense of how the word is being used in that specific sentence. At this stage, the paper applies something called a la carte transformation. What is this? A la carte is a technique that takes the information from the surrounding words and adjusts the base embedding of the target word in a very smart way, let's say. It essentially uses a learned transformation matrix to map the average of the context words into the same space as the original word embeddings. The result is a high quality, context-specific embedding of the target word, even if that word appears only a few times in the text. This is very important because in political texts, many words are rare and most contextual embeddings methods struggle with sparse data. Finally, what they do is simply run the embedding regression across all the dimensions to test whether the meaning differs across groups. Let's see here this in the first application. In the first application, the authors study how Democrats and Republicans use the word immigration differently in the US Congress. So the idea is simple. Every time the word appears in a speech, we extract its context embedding. Then we label these embeddings by party and run the simple regression. If the beta is large, this means that the meaning differs across parties. This allows us to quantify something qualitative in the sense of do Republicans and Democrats frame immigration in systematically different ways? This is what they answer. Here are the results. What we see by the nearest semantic neighbors for the word immigration for each party, we see that Democrats use immigration in a legislative and reform-oriented frame. Terms like reform, legislation, bipartisan, and so on. And in the other hand, Republicans, by contrast, use a law enforcement frame, words like enforce, laws, regulate, and so on. If we look at example context, the contrast becomes even clearer. Democrats emphasize comprehensive reforms, fixing the system, bipartisan cooperation, whereas Republicans emphasize enforcement, illegal behavior, and implementation laws. So, by this example, the semantic difference is strong and also statistically significant because they have confirmed this by permutation tests. This shows us how embedding regression transforms political language into some differences that we can measure in this case. Let's move on, to the second application of this paper. This second application looks at how the meaning of the word empire changes over time and also across countries, comparing speeches in the UK Parliament and the US Congress from 1935 to 2010. So once again, in this application, the authors extract context embeddings for each use of the word and estimate a regression comparing the two countries. This allows them to test whether the term empire carries different connotations in the UK and in the US, and whether these differences evolve over time. Let's have a look at the results and at the main finding. The results show a clear semantic divergence between the two countries. In this graph, the divergence become especially strong after World War II. This matches also with historical expectations. The UK gradually moves toward decolonization, while the US becomes a global military power. So, sorry. Again, the model is picking up a real historical evolution in how political actors use language. I have chosen also the third application from this paper. The third one asks whether the model can detect sentiment, positive or negative, in UK parliamentary speeches when talking about Europe. For each sentence containing emotional language, the authors extract a contextual embedding. So they are not doing sentiment analysis in a simple way in this case. Then they estimate a regression comparing negative versus non-negative context. This allows them to study how negatively toward Europe evolves over time without relying on a dictionary, which often misses subtle emotional cues. Here are the results about sentiment analysis that they have done. And in this slide, we have the results comparing the contextual embedding model in the first graph with the traditional dictionary approach in the second graph. The contextual method captures much more nouns. If we have a look at the graph, it detects subtle shifts in sentiment that the dictionary completely misses. It also performs well even when only a few examples contain emotional language, a very common situation in political speech. Whereas the dictionary method in the second graph, by contrast, is much flatter and less informative to us. Okay, this was the first paper. Now, let's move to the second one. This is another kind of application of LLMs in research. The paper has the title Demand Estimation with Text and Image Data. This is a paper in applied microeconomics. The aim is to rethink how we model consumer substitution when products have rich content like images, descriptions, and reviews that traditional models typically ignore. The authors propose a way to integrate this unstructured content directly into standard demand model by converting them into embedding. So in this case, the model is about what is the second choice of consumers when the first choice is not available. The core motivation of including this paper in my presentation is because this is a case we can understand why standard demand models rely on a very small set of manually collected attributes such as price, brand, size, rating, and so on. These are always the variables included in this kind of models. But real products, as we know, differ along many other dimensions, style, design, or text descriptions, or even perceived quality. These richer features are usually unobserved. So substitution patterns become unrealistic without including also these elements. The key idea of the paper is simple, but in my opinion, powerful. The use of unstructured information that already exists online, including images, descriptions, customer reviews, and turn them into embeddings. This is what they do. Then, after doing this, they plug these embeddings into the traditional demand system. So, embeddings here play the role of latent product characteristics that were previously unobserved. How do they transform text into images, text and images, sorry, into something unusable before, but that could be good in an econometric model. The authors, in this case, used pre-trained deep learning models. For images, they used standard CNN architectures. There are also some very good models that can transform images into embeddings. And for text, they used universal sentence encoder or sentence transformers applied to titles, descriptions, and reviews. So in this case, the model that they use is contextual embedding. In the first paper, the authors use static embeddings, whereas in this one, they use contextual embeddings. Each product gets several embedding vectors, each potentially hundreds of thousands of dimensions. To make this manageable, what they do is they simply apply PCA to each embedding source and keep a small number of principal components, let's say K components. In this case, in particular, they use three principal components. These three-dimensional vectors then become additional product characteristics, like in the same way like a price or a brand or other traditional variables. The key intuition is that substitution is driven by distance in embedding space, not only by a handful of manually selected attributes as was always done before. So let's see briefly the baseline model, only to have an idea. It's not the aim of the presentation to explain their model. This is the standard random coefficient logit model. Consumer utility is composed of mean utility, individual specific deviations, and an idiosyncratic error. The mean utility depends on observed product characteristics that they normally include in this Berry-Levinson-Pakes model that was introduced in 1995. The individual deviation mu IJT captures heterogeneous tastes by letting coefficients vary across customers. So, in few words, this is the benchmark model that authors compare their embedding-based model against. Now, here is the key extension. They augment the standard attribute vector with the embedding pieces, or in other words, the characteristics of the product now include both the usual attributes as before, such as price, the brand, the size, and also the latent attributes extracted from text and images. These embeddings enter the mean utility exactly like any other characteristics. They also interact with random coefficients, meaning consumers may differ in how much they value different latent dimensions captured by the embeddings. So this produces richer and in their in their idea more realistic substitution patterns. We will see also in the results that they present. But for evaluating the model, the authors ran an online experiment where participants choose a book. Because the prizes and the rankings are randomized, they can observe a real substitution behavior. So in order to validate the output of embeddings models, they run this experiment to say if the results were accurate or not. The big finding is that embedding-based models outperform both plain logit and attribute-based mixed logit. The best specification uses customer review embeddings, and not only the title, or not only the description, because customer review embeddings capture a fine-grained sentiment and perceived book features. So these models deliver the lowest archaic information criterion and also the lowest out of sample root mean squared error. So by this example, the overall takeaway is that unstructured text and also images can replace or also complement manual product attributes when estimating demand in this case, producing much more realistic substitution patterns. This is what they do. Okay, now it's time for the last application. After reviewing two different examples of how embeddings can be used in research, the first one, context embedding, where in the first paper, when embeddings are treated as the dependent variable to study differences in meaning across groups, and in the second paper, the demand estimation paper, where embeddings are incorporated as independent variables to improve prediction, we now turn to the last application. In this case, the focus is not on modeling, but is on data extraction. This is a work titled Leveraging Large Language Models for Structural Data Extraction from Regional Policy Documents. As I said to you before, this is part of our ongoing work on evaluating transition policies in Italy, part of Potion project. The goal here is to construct a reproducible pipeline that can take long, heterogeneous regional policy documents and convert them into structured and comparable data sets. Later on, such dataset allows us to systematically analyze how different Italian regions interpret and implement green and digital transition priorities. Now, what we do concretely is we apply the pipeline to the European Regional Development Fund calls from for the period 2014 up to 2020. These calls are long and complex policy documents. They are legal texts, often with dozens or hundreds of pages, with highly variable structure across the regions. Information may appear in the main body of the call, but also in the footnotes, in annexes, or attached tables, making manual extraction extremely time-consuming and difficult to standardize, but not only manual, also the traditional methods to extract the information was difficult to apply. Well, what we want is a single harmonized dataset that captures the key elements of each call in a comparable way. To achieve this, we rely on ChatGPT 4.0 version through the OpenAI API, not as a generative tool in this case, but as a controlled extraction system. We provide the model with a strict schema. We have 9 predefined sections that are part of our prompt, which is quite long. We will have a look at it now. We prompt to extract information about the objectives, about beneficiaries, about location rules, financial details, and references to smart specialization strategy in our case. And large language model, in this case ChatGPT, must return its output in a precise JSON format that fits this schema. Once defined, the same procedure can be applied to other policy documents as well, ensuring consistency and scalability across regions and times. Now, in a moment, I will walk you through the entire pipeline directly in Colab, so we can have a look at how we can integrate the large language models in softwares like Python in order to make data extraction. Let me close for a moment the presentation and let's access the Colab. Okay, we need to reconnect. Okay, I have prepared all the script here. So, as I said to you, we have some policy documents that are very heterogeneous. In order to create an idea, let me firstly show you two examples about the documents we are working on. I've chosen these two documents. These are calls from Regional Development Fund. For example, this is a call. It has 44 pages in total from this Valle d'Aosta region. And this is the structure of the call. And the other call is from another region, from Campania. It has in total 54 pages, and it has also a different structure. So this is these are our documents we're going to process. What I'm showing to you is the code in Python, and the idea is to see how we can integrate a large language model, in this case only using the prompt without fine-tuning, in order to extract data based on a research idea that we have to study sustainable transition in Italy. Okay, as in all other scripts in Python, we need to install the libraries. I'm going to show you only the library related to the LLM, which is OpenAI. This is necessary to install in order to call the GPT model. And what is necessary also in this case, if we want to create an automated pipeline that includes not only one document but lots of documents. In our case, we have a total of nearly 600 PDFs. We need to create an OpenAI API key in our OpenAI account. In this case, this is the OpenAI key. It is we need always to have this code and not to share with others. But in this case, I have deleted it, so it's not a problem about privacy. In this case, as I said to you, we have used GPT-4o, and we set the temperature equal to 0 in order to have very deterministic output. So we don't want our model to be creative in our case, because what we need is to extract the data as they are in the documents. The most important part of the whole script is this step 3 here, the prompt. So as you can see, this is a prompt in Italian because our documents are in Italian. And in a very natural and written in sentences, we have defined this prompt. This is quite long, but we have done lots of tests after before deciding which is the prompt that is okay for our case. Here we have assigned a role to our LLM, saying that it is an analyst for extracting this kind of documents. We have also included the format of our output. We want the output to be in JSON in this format based on the sections. And here are all the questions that we are asking from the LLM to extract. And all other steps are the necessary steps to refine and to include all the necessary elements how we want the output to be. Okay, what I want to show to you now is the output. In this case, considering the fact that the documents are quite long, as I said to you, the first and the second one has 44 and 50 pages nearly. We have applied the chunking strategy in order, because large language models can work better if we chunk the documents, and because if we tell the model to work in the entire document, maybe the output is not accurate. Here, the model have processed the first document. These are the chunks related to this first call. The same thing has done for the second document, and asking to have the output in JSON, we have this final output for each section. In this case, in our specific case, we have extracted textual data. So, for example, the first question was extract the aim and objective of the call as it is written exactly in the call without summarizing or paraphrasing anything. And we have this output, the whole part about objectives and the aim. We have also extracted other elements, for example, which are the beneficiaries, if the beneficiary is a company or not, asking the model to reply with 1, 0, or not available if the information is not present in the text. Okay, now let me turn back to the presentation. Okay. Now, as we wrap up, I want to point out that the presentation ends with this slide, collecting a set of key references from the recent literature. As you can see, all these papers are all recent literature because the topic is new. These papers include works on how large language models are being used in computational social science, studies on their performance in coding tasks, applications in economics and political science, and also methodological reflections on using large language generated variables in downstream analysis. There are also available other papers, but this provides a solid entry, in my opinion, entry point into the rapidly growing research landscape around large language models, embeddings, and text as data methods. Now, I think that I will stop here. Thank you very much for your attention. I hope the examples have given you a sense of how these tools can be used in research. I'm very happy to take any question or comment or idea. And of course, if you'd like to follow up afterward, you can always reach me out at my email. Thank you very much.
Thank you, Loreta, for your presentation and your nice introduction to the topic. There are a few questions on the chat and on the question answering panel. The first, I think, if I move to the question answering mode, there is one question by Mario Paolucci that asks what are the EU-based providers that are available. It refers specifically to one of your slides, namely slide number 30. You were
Sorry?
presenting something. You were presenting something
Sì.
about the EU providers, and he's asking if what are those providers?
Yes.
Yeah, yeah. Here, the question if there are EU providers that are available for this part on data privacy and compliance, if any, of
No,
course.
yes, this has to be, this is related to the limitations of large language models about data privacy. And yes, you can, if you have a big a project and the data that you are processing has to do with privacy concerns, it's good to ensure that all the pipeline is secure, and in the sense that you need to be okay with all the regulations before using the data into an LLM. And there are, I cannot mention something in specific, but there are some rules that we need to follow in order to be okay with all the elements.
Okay. Just a note, I just allowed Mario to use his mic if he's willing
Yes.
to ask something more specific or rephrasing my question or my understanding of his question. I don't know if Mario wants to reply.
Yes.
Well, that doesn't answer the question, which was where are these EU-based providers? Because actually there's none. And it was kind of a provocative question. Also seeing that you list this in your best practice, but in practice, nobody does the best. Everybody just goes to ChatGPT or Anthropic.
Yes, but
and that's a big for
yes,
me a big ethical issue. And I was wondering if what's the status of Mistral, but I understand that probably we've lost Mistral as well. That's it.
Yes, yes, yes. The idea is that we focus in the big models, but there are also some smaller models, or we can create in some way our models, fine-tuning the existing models, and we can also run the models locally. Okay, if we choose to run the models locally, we cannot use the big models as ChatGPT locally. But this is a trade-off. If we are interested in automation or more accurate results without considering the limitations, we can address our focus into the big models, ChatGPT, Llama, and so on. Or if we are more concerned about data privacy and security, we can rely on smaller models, but they are not able to give us maybe high accuracy. So it's a trade-off, and we need to make a decision.
Salvatore, you want to ask something? I see your hand raised.
Yes. No, I don't want to ask a question, but actually I want to thank Loreta for the very useful and very clear presentation. It was extremely clear, extremely useful, even for me that I'm not in this field. It was extremely useful, and also I think that you highlighted very well the interdisciplinary aspects of this kind of models, how they can join different disciplines. So for us, for the department, is extremely useful. And I exploited this minute you gave me, Andrea, to propose something that, of course, we will discuss, but I would like to put this presentation online in on our website, and also if you Loreta send us not only the presentation, but if you have a material, we can create a space on our web.
Yes, of course.
Yeah, we can add this kind of material to your presentation. And of course, I invite you if you have, I don't want to give you other job, but if you want to make a follow-up, I will be extremely happy to follow again. I followed almost from the beginning. I just lost the chair. I asked Giovanni to introduce the course, but then I was lucky and I managed to follow almost all the course. So I was happy I managed to do it. So thanks again for in the name of everyone, Loreta.
Thank you very much, Professor. Yes, I was thinking about another seminar, and it would be great if we concentrate the next time in fine-tuning the models, because as I said, we can use the models as they are, and it's okay. But if we want to adapt the models based on our specific research objectives and necessities, it's very useful to fine-tune them and to use them as we want for our objectives.
Thanks.
Okay, thank you. There are a few questions that some participants are posting in the chat. I would go in this order. I will enable the mic of the participants that are asking questions in order that they are able to ask the question personally. So there's one question by Ilaria Falvo. If you give me just 1 second in order to enable your mic. Yeah, I found you. So Ilaria, you should be able to open your mic now. In a way, you can ask your question to Loreta.
Can you hear me?
And then there is also one hand raised. Yeah, it's...
Okay, perfect. So hello, Loreta. I'm Ilaria here. So really, really interesting presentation, and thank you for suggesting the participation. So I'm actually under this, I can say, basically the same situation in that I'm really dealing with a bunch of data that it's actually constructing my database. And my question is relevant. So if I'm starting from this database that is linked to a set of guideline statements that are provided online, so I can give for example, the link where I can find it. But others are in a PDF that I'm saved in my directory in my computer. Does this work in any case with this different allocation of the data?
Yes.
And second, just to conclude, is also working for my pictures, because I definitely would like to having a screenshot and have a list of pictures that are both in the PDF and the link.
Yes.
Okay, great.
Thank you very much, Ilaria. I'm happy you are here today. Yes, we had the same problem as you, because the PDFs that I showed to you before from regional funds were, some of them were in pictures, so we need to pre-process them before sending to ChatGPT. You can pre-process using optimal character recognition techniques, and later on you can use them as PDFs. And related to the first question, if you have some documents in links and other in PDFs, it's not a problem. You can include in your script different sources of documents.
Thank you.
Thank you.
Okay, there is also another question. I see an hand raised, and is Fulvio. Fulvio, I enabled your mic, so I mean enable you to open your mic. So if you want to ask your question, you can unmute and speak. So Fulvio, can you hear us? Okay, we can queue Fulvio question. There's any other question, or if you want to ask a question, just raise your hand and I will enable you to speak and open your mic. So just raise your hand on Teams. So in the meanwhile, I have a question to Loreta that is related to one of the aspects that she were referring to. So using large language models as tools for performing data extraction or knowledge extraction, which is, I mean, one of a very interesting aspect. There are, in my opinion, two things to care of. So the first, in many cases, there are already solutions that are not based on large language models that are qualitative in the sense of performance in terms of knowledge extraction or data extractions. So why we should opt for large language models instead of existing approaches if they are already able to perform, for instance, named entity recognition and linking, which is one of the tasks that is typically associated with knowledge extraction. The other point is that in some cases, large language models, I mean, not in some cases, in all cases, large language models are generative. That is, if we opt for tasks that are focused on data or knowledge extraction, what we can have as an output is that we have new knowledge instead of the knowledge that we are looking for to be extracted, which is new knowledge that comes from the generation process. So how we can mitigate this, if you have any idea or your experience
Yes.
of what you did.
I can talk related to my own experience in the Potion project. We started by implementing traditional methods for data extraction that are rule-based methods, or keyword extraction that could extract entities or events or relations. But it was challenging because, as you know, if we implement rule-based methods, they don't understand the context. We need to make lots of pre-processing steps in order to put the rules about what we want to extract and how we want to extract. And considering the fact that our starting point of documents, so the documents we had in our hands were very heterogeneous in the sense that in Italy there are 20 regions. Inside the regions and inside the regional funds, there are lots of topics included. For example, some calls talk about energy, others about training, others about mobility, and so on. So it was we were in front of these documents, one different from other, and it was quite impossible to implement traditional text mining methods to just extract the data. And considering the fact that they extract, but in a manual, in a mechanic way, can I say, and large language models can understand the context, we decided that it's the best way for our case. But also in the literature, because I have studied a lot also about the project, there is a huge and increasing literature that has applied data extraction, especially in domains where unstructured data is present. Because if we have data that are in some way standard, we don't need to apply large language models. It's okay to apply the traditional methods. For example, in medicine, in finance, in law, there are lots of implementation of data extraction using large language models, and the results are quite impressive. I can mention accuracy nearly 97%. That it's okay. It's let's say it's an acceptable level of accuracy. And I think also in the domain of policy evaluation, where the documents are very heterogeneous, the data are unstructured. It's a good way to use large language models in extracting information.
Okay, thank you. So I don't know if you can read the question asked by Fulvio, and the question is, I mean, I can read for all the participants. The question is, AI agents represent the latest frontiers in LLMs. What are the possible uses of AI agents for social science research? How would they extend the uses that you have presented here or allow for new applications?
This is a very good question, but as I said, that LLMs have their own limitations. I have my limitations in this field. I have a background in finance, economics, so I don't know how AI agents work. To be honest, I know that they are specialized in specific tasks. So I need to study. Maybe it's my next step in this learning process.
Okay. Don't know if there's any other question from the participants. I retrieved, so that there is one question asked by a participant, I can read Moreira, and it was asking, or she was asking, I don't know if, I don't want to make a mistake, but I mean, the question is, how is LDA comparable to BERT for topic modeling? I don't know if you answered in the meanwhile to this question, Loreta, but this question was asked 1 hour ago in the chat. Maybe it remained unanswered, or I don't know if you can answer it now.
Yes. Thank you. Yes, LDA versus BERT. As I said, BERT is a model that in its structure has the transformer architecture. So when we apply BERT in sentiment analysis, we are the model can understand the context. So through embeddings, the output is more. It represents the context better compared to traditional ADA.
Okay. Thank you. I mean, I noticed that while you were presenting, you also shared some notebook, some code written in Python specifically.
Yes.
I have a broader question. So if there's any of us that is interested in what you are doing and wants to start a collaboration, I mean, if is there so what is the right approach besides obviously contacting you? I mean, are you sharing or your work on archives like GitHub, or I mean for what concerns software?
Yes, yes.
Okay,
Yes,
so
referring to this, as I said, the work that I presented is under review. It will be soon published in it's a book. It's part of a book chapter, and related to this publication, we will also publish all the scripts in GitHub, so it will be available there. You can access it there.
okay. Any other question? Don't be shy, obviously. Okay. Okay, if there's no other question, I have a curiosity. So in this case, I will ask you another question. That is, I mean, I saw that, I mean, you are using LLMs in different domains, okay? It can be, let's say, economics or legal. So is there any domain in which, I mean, you have the perception that LLMs are more effective for specific tasks, or basically they are good enough in any of the domains that you experimented with?
I don't know if they perform better in one specific domain or worse in another. But I think it's not the domain that defines the performance. It's the way how we implement an LLM. We need to know all the potential that they have, but also all the limitations, the ones that I included in my presentation, but there are also more others. We need to study before all the potentials and also the limitations, and the domain it's not important.
Okay, thank you. You fully answered my question. I agree with you totally. So I tried to be provocative, but I didn't succeed in my provocation. So I thank you, Loreta, for your brilliant presentation. Very clear. Everything was clear and also nice presented in a way that, I mean, you were able to foster, the interaction, and also, allow participants, I would say, that were not fully focused on the domain or on the topics to be involved in. So thanks again, and have a nice day and week. Today is Monday, so we have a whole week to go ahead. So Carla, I see that you raised your hand. I don't know if okay, no, it was a react. Okay, good. So thanks again to our presenter. Just a last but not least information, as already Salvatore said, we will do our best to publish both the presentation and the slides on the web channels, that is either or both the website and the YouTube channel we have as department. I'm saying we will do our best because I don't know if there will be any technical issue that will prevent us to publish the presentations, but I am confident that we will be able to. So everything will be available as soon as possible. So thank you again, and bye-bye. See you next time for the next course of the department.
Thank you very much, Andrea, for your support. Thank you, all of you, for attending the seminar. Bye.
Bye.